Hey guys, in this video I'm going to be talking about dot products, and I had mentioned that last time. You might also hear them called scalar products, or even in some fields of physics you might hear them called inner products, but it's all really more or less the same thing, and that's going to be a dot product. And so what you might recall from last time is that we had vectors and we had scalars, and vectors are going to be something like these v's that you see here, where it's going to have several components, and scalars that you could represent by alpha, or any number or any other letter. And if you're confused about that, then you can watch my last video. But yeah, so what a dot product is it's a way to essentially multiply two vectors together. So if you were to multiply two scalars together, that's simple. That's just multiplication. That would be like if you were to have 5 times 6, 5 times 6, well, that's 30 if you remember your times tables, and if you don't, you can plug it into a calculator or look it up. But what happens if you have, like 5, 3, 1, and you want a dot product, you want to dot that with another vector, say 7, 2, 0. And that's that's a little bit different. It's a little bit of a question, because it's not just a simple multiplication now. And it turns out that there is actually an operation that is defined as this operation right here, and that's called a dot product. And so what you're going to do is essentially multiply them component-wise and then add them together. And might sound complicated, but it's really not bad. And so I think probably the best way to explain this is to look at an example. So let's say that we take one vector here, and we're just going to make this an x1, x2 vector, and we want to dot that with another vector. Let's call it y1, y2. And so these x's and y's, they could just be any number. And so what we're going to do is we're going to take this x1 and we're going to multiply it by this y1. It's the same component. It's this first component. So we're multiplying the first component of the first vector by the first component of the second vector. So the first term that we're going to get, I'll write it in red so you can see there, is x1, y1. And then what we're going to do is we're going to multiply the second component. So we're going to multiply the x2 component with the y2 component. We're going to multiply these together, and we're going to add that to our first component, plus x2, y2. And like I said, it's just a very simple operation here, and multiply them component-wise and then add the results. And if you were to have, say, 3 or more components, it would be the same thing. If we had x3, we would multiply it by y3, and so on and so forth. And so one of the things I mentioned at the beginning is that this is also called a scalar product. A scalar product. And the reason for that, you may notice, is that if you look at this operation here, oops, I didn't get a C in there. If you look at this operation, so if you look at this x1, y1 plus x2, y2, so this dot product here, that's going to come out, well, it's going to come out to be a scalar. That's not going to be a vector. You're going to multiply two vectors together with a dot product and end up with a scalar. And so it's called a scalar product. And we'll talk about it later. There's something called a vector product, which is, it's a similar operation. It's also called a cross product. You may have heard of them, and but you'll get a vector out of it. But that's a different operation. I'll do a different video on that one. But for now, we're just dealing with the scalar product. So multiply component-wise and add them together. So for a more concrete example, I suppose we could go with, like, say 3, 2. This is going to be our vector v. And let's say our vector u is 1, 0, and we want to look at v dot u. Alright, so what's this going to be? Well, you know, before we had this 3 and this 1, so we're going to multiply the 3 and the 1. We're going to get 3. 3 times 1 is 3. And we're going to add it to 2 times 0. And so that's going to be 0. So 3 plus 0 is just going to equal 3. This is going to be v dot u for these two given vectors. And I guess now I should probably talk about a couple properties of the dot product. So properties of the dot product, if you have a vector that is dotted with it 0, so if we have v dot the 0 vector, so the 0 vector being, you know, any number of components, but their entries are all 0, etc., etc. It could be 2 components or it could be infinite. Then this is going to equal 0. And that's pretty easy to see. If you multiply component-wise by zeros, then you're going to get 0 plus 0 plus 0 plus 0 plus 0, etc. Alright, so the next one I want to talk about is if we have u dotted with v and multiplied by some scalar, well, that's the same as scalar times u dotted with v, which is pretty nice and also expected. You know, all of these properties are going to fall out of the same properties that we've had for many years when working with numbers, which is, you know, distributive, associative, these type things. And similarly, actually, if you have u dotted with w plus v, well, that's going to equal u dotted with w plus u dotted with v. And again, this is a pretty simple thing to see, pretty intuitive thing to see, I think. And it's a property of the dot product. It is I believe this is the distributive property. You can distribute it across the parentheses. And another property, which is maybe a little bit less easy to see, is that a vector dotted with itself, so if we have v dotted with v, that is going to be the length of v squared. These two lines here, these just indicate that it's the length, the magnitude. You might or might not have seen those before. But anyway, you can also just write it with 1, depending upon whether you're a mathematician or a physicist. Mathematicians tend to write it with 2. Physicists tend to write it with 1. That's the magnitude squared, though. And the reason that this is the case is essentially the distance formula. If you remember that, you know, if the distance between 2 points on an xy plane, if we have a point here and a point here, well, let's say that this is 1, 3, and that this is let's say 4, 1. Well, the distance between these points is just going to be the distance formula. So we're going to subtract one from the other. So we're going to have, you know, 4 minus 1 component-wise. So 4 minus 1 and well, yeah, and then 1 minus 3. So we're going to have 3 and negative 2. We're going to square them, add them together, and then take the square root to find the distance. Right? You probably remember this formula. If you don't, this is called the distance formula. You can look it up if you're confused by this, and it's essentially from Pythagorean Theorem. You could also draw a triangle and do it like that if you got confused. You know, a squared plus b squared equals c squared. But anyway, what you might notice though is if we have two vectors that are the same, if we have v dotted with v, then all of these components, they're going to be exactly the same. So we're going to have, you know, the length of v is, let's say that v is some point, x1, y1, well, up here maybe, and this is our vector v equals v, and so the length of this is going to be the same thing. You're just going to use a distance formula. So you're going to have your x1 squared plus your y1 squared, and you're going to take the square root of that. And again, you can see this from the Pythagorean Theorem, which would say, look at this triangle here, and a squared plus b squared equals c squared. Well, all right, if we square this distance term, so we're looking at the distance squared, then we're just going to end up with x1 squared plus y1 squared. Well, let's say we're dotting v with v, so v dotted with v is x1, y1, dotted with x1, y1, that's a y, y1. Well, like we had said before, multiply component-wise, x1 squared plus y1 squared, and it's exactly the same. And so that is where this property comes out of. V dotted with itself is going to give the length squared. And maybe what I'll do next time, actually, if I don't get to cross products, is go ahead and show you there's a formula for the dot product. V dotted with u is equal to the length of v times the length of u, so still vectors, times the cosine of theta, where theta is the angle between v and u. So if we have our vector v and another vector u, and we dot them together, then the sum of that dot product, the scalar that we get out of that is going to be the length of the v vector times the length of the u vector times the cosine of theta, where theta is this angle in between the two, and that's a theta. And like I said, next time I can go ahead and I can prove that for you guys. And we can also look at the projection theorem as well, which is the definition of projecting one vector onto another. So just looking ahead a little bit, but for now I hope that that helped clear things up a little bit, and you guys take care. All right.